Ronnie, before we get into the discussion of the Brojde Centre and its research, your own research has been quite spectacular and innovative. How did you first get into your ideas of optics and electronic transference and all the kind of work you're doing? What was that led up to your innovations?
As a matter of fact, I don't have a good answer to this. And I was always interested in the top-down approach to the problem I was working on, looking for ways to implement my ideas, regardless of my basic expertise. I'll give you an example way back from when I was a postdoc. Okay? I did my PhD in solid-state physics, working in nonlinear optics. And after I graduated, I went to Caltech to be a postdoc. And this was in the mid-80s or so. And at the time in Jerusalem, at the Hebrew University, people developed theories about neural networks. They thought perhaps that since there are so many nerve cells all interconnected, they can look at neural networks as a huge cluster of interacting particles and apply statistical physics methods. And they came up with very fascinating theories here at the university in '85. And I was interested, I was asking myself how I can build such a network, regardless of the biological implication of these theories, okay? I thought maybe if I can build it in the lab, I would have a very nice, computing machine to play with. And I was working in optics, and so of course I started looking into optical ways to do it. But I realized that actually I came across an idea in electronics how to do it, and I didn't know much about electronics at the time, at the depth that was needed to build such a thing. So when I came to Caltech, I went to my mentor at Caltech, and I told him, look, I know you brought me here to do nonlinear optics, but I have these ideas in electronics. Maybe I can do it too. And he encouraged me to do it. So the bottom line is that I'm looking at the problem in general terms, and I'm looking for the optimal way I can approach it, regardless of the means by which I'm going to approach it. So I switched completely to electronics, and I built these networks. And
describe the networks, because it's hard for a layman to understand. I read some of it, and you're known for the inventor of electron holography.
Yeah, the electroholography, strangely enough, came out of this. I was working in parallel to as I said, to my work in electronic neural network. I was working in nonlinear optics in developing materials that can be used for holographic memories, okay? And at some point, working on these electronic networks, I thought that maybe I can boost up the performance by using the holographic materials, okay, to build the neural networks. And what I was looking for is a way by which I can build an electronic neuron connected by a hologram to many other neurons. And for this, I had to control the hologram electrically. And this was how electroholography came about. But interestingly enough, when we were looking for application for it, when it became mature, it went to an entirely different space, to the space of optical fiber networks in telecommunication, where it made its mark.
It revolutionized the field of communication.
In a sense, yes, but unfortunately, in 2001, the telecommunication world crashed, and the business models that needed electroholography were not developing into what they were supposed to be developed. So we are still waiting for these things to be used. I'm sure it will be. It was simply before its time.
Now, you're into, in the center, you're into whole new things on sensing and sensing in the skin that you described.
Yes.
Describe
This
in
is
layman's
exactly.
language if you can.
This is exactly an example of the same pattern. If you look at the internet today, at the internet 15 years ago, okay, so you had a computer on your desk and with a monitor, a keyboard, connected to the network, a mouse, and this was the node of the internet, the classical node of the internet. And today, every cell phone is a node in the internet, and so it's mobile now, okay? But over the past decade or so, there is a new trend that is starting to happen, and that is that we want to merge the cyberspace with our living environment. And for this, we had to add to the two foundation elements of the cyberspace, namely computing and communication. We had to add an additional element that will enable us to interface our living environment with the cyberspace, and that is sensing. And now sensing is a totally new game, because if you look at computing, for instance, digital electronics, it is based on a fairly narrow spectrum of physical phenomena, namely conductivity in silicon, related materials, and so forth. Now, sensing is something else entirely. We have to import a very broad spectrum of phenomena from the realm of basic research into the arena of engineering. Okay, so we are looking at a wide spectrum, very different types of phenomena.
So this
into
enormous
different type of spectrum. And what you ask, our sensing of the mental state is I think is a good example of this. My colleague Yuri Feldman, who was working on the electric spectroscopy, looking into ways to monitor the glucose in the bloodstream, non-invasive monitoring, another type of sensing, came across images of the skin organ done by what is called optical coherent tomography that allows you to look 1 millimeter deep into the skin. And when you look at these images, you see that the tip of the sweat ducts that lead from the sweat glands to the pore at the surface of the skin, the tips looks like small coils. And
so
if you
different than Gray's Anatomy.
yeah,
in
in Gray's Anatomy, it
it's
looks
not
like a straight tube.
That's right.
Okay, and here it looks like a coil. And if you look at these images, not in the eyes of an anatomist, but in the eyes of an RF engineer, it looks like the antennas that were used in the 70s. Of course, much smaller. Okay, and these antennas are called helical antennas, and they were used widely in the 70s and early 80s, less so today, but still. And so we were asking ourselves if these coils, they look like antennas, maybe they behave like antennas, and we started investigating this. We did a series of measurements, measuring the ratio between an incoming beam and an outgoing, and the beam that is reflected from the skin. And we saw that this ratio is very much affected by several biological, physiological parameters, like the blood pressure, the pulse rate. So we went a step further and we started doing tests of emotional stress. We learned from psychologists how you can produce emotional stress in a controlled manner. And we saw that these signals also indicate the emotional stress of people.
You're telling me that the body is a sensor and reveals and sends off how they feel, if they're in love or if they're scared or anything like that. And you can pick it up.
Yes. First of all, I must say that this is something very preliminary. I mean, we just started the research, we published a few papers, it aroused a lot of interest, but there's a long way to go. But yes, we have very convincing experimental evidence showing that when someone is being stressed, we see it in our signals. And mind, this is a remote sensing capability. In other words, I can look at someone from a few meters away and tell you this guy is agitated.
Right.
Okay? Of course, I cannot go much beyond that, not for now at least. I cannot tell you someone who's boarding an aircraft, if he's going to do something bad, you know, to this aircraft, or he's agitated because he has a job interview a few hours away. This I cannot tell you yet.
But the future
But
is
the future.
But the future is people walking around, all as nodes in this network, in which a central network can read how everybody's states are. So I can wear something and find out if this girl really likes me or not. It's possible.
Okay, this
right?
is okay. Let's put it in proportion. This is a sensing technique that we're developing. It's in very early on. The future looks very interesting, at least, but there's a long way to go.
I realize that.
But the thing to remember is that we should look at the nodes of the internet exactly like that. They are sensors with computing capability that are all interconnected. I'll give you another example.
You'll have to be very brief.
Okay. So there is a sensor that we develop in my lab now, and where we use live microbes as the sensing element. Live microbes, we look at them as minute biochemical laboratories. They are genetically engineered to detect the presence of the substance they're supposed to detect. And when they detect the presence of the substance, it is manifested by the microbe changing its optical quality. And in my lab, my students are building the optoelectronic environment around this microbe. So think about it. It's a device that has a biological hard core, but it's optoelectronic, and we have to encounter the system engineering which puts together a biological entity with a technological
With the
entity.
computers and the rest of it.
Computer,
Communications.
communication, and the interface between them.
Wow.
Okay?
It sounds
So-
revolutionary. But we'll have to end there, and I'm going to read your papers because I think this is fascinating stuff.
Okay.
Thank you for coming.
Thank you.